Welcome to this comprehensive guide on Agent Lightning, the absolute trainer to light up your AI agents. Agent Lightning lets you train any AI agent with reinforcement learning without changing a single line of your agent code. Whether you use LangChain, OpenAI SDK, AutoGen, CrewAI, or Vanilla Python, Agent Lightning works seamlessly. Let us dive in. Training AI agents is a major challenge. Out of the box, agents are powerful but unreliable. Developers spend hours manually tuning prompts, which is tedious and fragile. There is no systematic way to improve agent performance over time. And when you have multi-agent systems, optimization becomes even more complex. Agent Lightning solves this with a principled, automated approach. Before we dive into Agent Lightning, let us understand reinforcement learning. In RL, an agent takes actions in an environment and receives rewards based on how well it performs. Think of it like training a dog with treats. Good behavior gets rewarded, and over time, the dog learns what works. Unlike traditional programming where you spell out every step, in RL you define the goal and let the agent figure out how to achieve it. The key terms to remember are agent, environment, reward, and policy. Agent Lightning provides zero code change reinforcement learning training. You do not need to modify your existing agent code. Instead, you use lightweight decorators to emit training events. You can selectively choose which agents to optimize in a multi-agent system. The framework automatically tracks performance and improves your agents over training iterations. The core architecture of Agent Lightning has 4 key parts. First, your agent emits structured spans via lightweight helpers or tracers. These flow into the Lightning Store, a central hub managing tasks, resources, and traces. Then the algorithm reads these spans, learns from them, and posts updated resources like refined prompts or policy weights. Finally, the trainer orchestrates the entire training loop, coordinating datasets, resources, and inference updates. A training loop is the core cycle that makes agents smarter over time. You run the agent, evaluate how it did, improve its strategy, and repeat. Think of it like taking practice tests before an exam. Each round reveals weaknesses and helps you improve. In Agent Lightning, we batch many examples together so the agent gets a stronger learning signal. One full pass through all your training data is called an epoch, and typically you run multiple epochs to reach peak performance. Execution bundles are a key concept in Agent Lightning. They group multiple agent execution runs together as a training unit. This enables batch-level reward computation, where you evaluate agents across many tasks simultaneously. Bundles also enable efficient parallel training execution, making the most of your compute resources. Spans and telemetry are how Agent Lightning observes your agent in action. A span is a structured log of every step, capturing inputs, outputs, timing, and decisions. Think of it like a flight recorder for your AI. It records everything so you can analyze what happened after the fact. This observability is essential because you simply cannot improve what you cannot measure. Agent Lightning uses spans to power its learning algorithms. Tasks represent individual challenges or inputs for your agent. Spans capture structured telemetry for each step the agent takes during execution. The training loop follows a simple cycle. Run the agent, evaluate its output, learn from the results, and repeat. Over iterations, the agent progressively improves. This structured approach to telemetry makes Agent Lightning compatible with any framework. Training an AI agent generates a lot of data: tasks, results, metrics, traces, and more. You need one central place to store all of this consistently so nothing gets lost. A central data store also enables distributed training, where multiple machines can read and write training data in parallel. Think of it like a database for your experiments. It keeps everything organized so your algorithms can learn effectively. The Lightning Store is the central hub of Agent Lightning. It provides a unified interface for managing all training data, including tasks, resources, and execution traces. You can choose between an in-memory backend for quick local experiments or MongoDB for persistent, distributed setups. The store also exposes a REST API, enabling client-server architectures where agents and trainers run on separate machines. Agent Lightning supports 6 major frameworks: LangChain integration uses a callback handler. OpenAI Agent SDK has native support. AutoGen provides multi-agent framework integration. Crew AI enables team-based agent optimization. Microsoft Agent Framework is supported. And Vanilla Python means you can use Agent Lightning without any framework at all, making it truly framework agnostic. There are two main approaches to improving an AI agent. Prompt optimization changes the instructions you give the model, tweaking wording and structure to get better results. It is cheap and requires no GPU, but has a limited ceiling. Fine-tuning, on the other hand, changes the model weights directly, which is more powerful but requires compute. Agent Lightning supports both approaches, so you can choose based on your budget and performance needs. Let me explain exactly how automatic prompt optimization works. First, you must provide the initial prompt template through Initial Resources. APO does not generate one from scratch. It evaluates your prompt on sample tasks and measures the reward. Then an LLM, called the gradient model, critiques what went wrong in failed cases. It rewrites the prompt to address those weaknesses. Beam Search explores multiple candidate prompts in parallel and keeps the top performers. This cycle repeats until the prompt converges on the best version. It is important to understand what exactly gets optimized. With APO, only the text instructions you give to the model change. The model itself stays completely frozen. This means APO works with closed API models like GPT-4o and requires no GPU. With VERL, the actual neural network weights of a local LLM like Qwen or Llama are updated through reinforcement learning. VERL is more powerful but requires a GPU and an open-source model you can modify. Agent Lightning offers three optimization algorithms. First, reinforcement learning using VERL with PPO or GRPO, which trains the model weights directly. Second, automatic prompt optimization or APO, which uses Beam Search to find better prompts without changing model weights. And third, supervised fine-tuning or SFT, which trains on successful agent trajectories. Each algorithm suits different use cases and compute budgets. Agent Lightning supports two programming patterns. The function-based approach uses the add_owl.rollout decorator on a simple function, which is great for single agents and quick experiments. The class-based approach extends agl.lidAgent, giving you lifecycle hooks like onRolloutStart and onRolloutEnd, plus better structure for complex agents. Both patterns are fully supported across all optimization algorithms. The trainer is the orchestrator that ties everything together. You create an AGL trainer with your agent, algorithm, dataset, and configuration. Calling trainer.fit runs the full training cycle, iterating through your data and improving the agent. For debugging, trainer.dev runs a single rollout so you can test your setup before committing to a full training run. Agent Lightning has a growing research community. The foundational paper is on RxIve with ID 2508.036ATO. Community projects include Deep Werewolf, a Chinese werewolf game built with Agent Scope. Agent Flow from Stanford brings a modular framework with Flow GRPO, and U2 Agent has verified scaling to 128 GPUs for math, code, and search tasks. The project is open source under the MIT license. Let us start with system requirements. You need Python 3.10 or higher. Agent Lightning runs on Linux and Mac OS natively, with Windows support via WSL. A GPU is recommended for reinforcement learning training with VRL, but APO and SFT can run on CPU. For memory, plan on 8 GB or more for APO and 16 GB or more for RL training. Basic installation is simple. Just run pip install Agent Lightning. This installs the core framework along with APO support out of the box. It works with any Python environment, whether you use VNV, Conda, or Poetry. You will be ready to train your first agent in just minutes. For automatic prompt optimization, install with the APO Extra. Pip, install Agent Lightning bracket, APO bracket. This includes the gradient model dependencies needed for Beam Search prompt optimization. The great thing about APO is that it does not require a GPU, making it accessible for anyone with a standard development machine. For reinforcement learning with Virl, you need a few additional packages. First, install PyTorch with CUDA support. Then install FlashAtom with the no-build isolation flag. Next, install Velm for fast inference. And finally, install Virl itself. This stack enables PPO and GRPO training with efficient GPU utilization. For development setup, clone the Agent Lightning repository from GitHub. Use UV-Sync for fast dependency management and installation. You can run the test suite with PyTest to verify everything works. Contributions are welcome via pull requests, and the project follows the MIT license. Let us build your first agent with Agent Lightning. The room selector is a simple example where an agent picks the best room from a list. You define a rollout function decorated with an agil.rollout. The agent receives a task with room options, calls the LLM to make a selection, and returns the response. A reward function then scores how good the selection was. The @agil.rollout decorator marks your function as a training rollout. Inside the function, access the current task data via agl.task. You can use prompt template to create dynamic prompts that the optimizer can refine. The function returns the agent output, which the reward function evaluates. This simple pattern works for any agent, from simple Q&A to complex multi-step reasoning. You can add tool calls to your agent using the standard OpenAI function calling schema. The agent decides when to invoke tools during its reasoning process. Tool results feed back into the conversation, enabling multi-step workflows. All tool calls are automatically captured as spans in the training data, so the optimization algorithm can learn which tool usage patterns are most effective. The reward function is how you tell Agent Lightning whether the agent did well. It takes the agent output and returns a float between 0 and 1. You can implement exact match for tasks with known answers, use an LLM as a judge for open-ended tasks, or write custom scoring logic. This reward signal drives the entire optimization process, whether you are using RL, APO, or SFT. To set up automatic prompt optimization, create an agl.apo configuration. Specify the gradient model, which is the LLM that critiques and rewrites prompts. Set the beam width to control how many prompt variants are explored simultaneously, and num rewrites controls how many rewriting iterations to perform. APO is great when you want to improve agent performance without touching model weights. The AGIOM. Trainer configuration ties everything together. Pass your agent function, the algorithm, APO, RL, or SFT, and your dataset. Configure batch size for how many tasks to run per iteration and num iterations for the total training rounds. Optionally provide a validation set so you can track progress and detect overfitting during training. Call trainer.fit to start the training loop. The method returns training results, including metrics like average reward, best prompt, and training history. Progress is logged per iteration so you can monitor improvement in real time. Checkpoints are saved automatically, so you can resume training or use the best checkpoint for deployment. Here is a real result from training an SQL agent. Starting accuracy was 56.9%. After reinforcement learning training with Agent Lightning, accuracy improved to 72.1%. The reward curve shows steady, consistent progress across training iterations. And remember, this improvement was achieved without changing a single line of the agent code. LangChain integration is straightforward. Import the Agent Lightning callback handler and attach it to your LangChain agent or chain. All intermediate steps, tool calls, and LLM invocations are automatically captured as spans. This also works with LangGraph, so you can train graph-based multi-step agents seamlessly. Agent Lightning has native support for the OpenAI Agent SDK. It intercepts API calls transparently, capturing all conversation turns, function calls, and tool usage. The full conversation history is preserved as structured spans, giving the optimization algorithm complete visibility into the agent decision-making process. AutoGen integration enables training of multi-agent conversations. Each agent in the group gets its own span context, so you can track individual contributions. You can selectively optimize specific agents while leaving others unchanged. The full group chat history is preserved, enabling the algorithm to learn from successful collaboration patterns. Crew AI integration lets you optimize team-based AI crews. Each crew member agent can be individually optimized for their specific role. Task delegation patterns between agents are captured as structured telemetry. Over training iterations, the crew learns to coordinate more effectively, improving overall team performance. Microsoft Agent Framework is fully supported through a plugin-based integration. This enables enterprise-grade agent optimization within the Microsoft ecosystem. It is compatible with Azure deployments, making it a great choice for organizations already using Microsoft infrastructure for their AI applications. If you do not use any agent framework, vanilla Python integration is available. Use agl.emit for manual span creation, giving you full control over what gets tracked. This is the lightest weight integration option and works with any Python code, including custom LLM wrappers, API clients, or bespoke agent implementations. Let us dive deeper into automatic prompt optimization. APO uses Beam Search to explore the prompt space efficiently. Multiple prompt variants are evaluated in parallel against your dataset. An LLM serves as a critic, analyzing failures and rewriting prompts to address them. The best performing prompts are kept and refined further. No GPU is required since APO works entirely through API calls to language models. The APO workflow has 3 steps. First, evaluate the current prompt by running the agent on tasks and measuring reward. Second, the critique step uses an LLM to analyze failure cases and identify patterns in what went wrong. Third, the rewrite step generates improved prompt variants based on the critique. This cycle repeats for each Beam Search iteration, progressively discovering better prompts. Key APO configuration parameters include Gradient Op Model, the LLM used for critiquing and rewriting prompts, typically GPT-4 or similar. Beam Width controls how many prompt variants are explored in parallel. Num Rewrites sets the number of optimization iterations per beam step, and eval samples determines how many tasks are used in each evaluation round. Tuning these parameters balances optimization quality against API costs. VRL brings reinforcement learning to Agent Lightning by directly updating model weights. It supports both PPO, Proximal Policy Optimization, and GRPO, Group Relative Policy Optimization. VERL uses VLLM for fast inference during rollouts and flash attention for memory-efficient training. This combination enables training agents on complex tasks where prompt optimization alone is not enough. VRL configuration has 4 main sections. The Data section configures your dataset and batch sizes. The Actor section specifies the model, learning rate, and optimizer settings. The Trainer section controls epochs, gradient accumulation steps, and checkpointing. And the Rollout section sets generation parameters like temperature and max tokens. These parameters give you fine-grained control over the RL training process. Supervised fine-tuning is the third algorithm option. It trains on successful agent trajectories, teaching the model to replicate high-reward behavior. Agent Lightning integrates with Unsloth for memory-efficient fine-tuning. SFT is great for distilling knowledge from large models into smaller ones, and is the fastest training option when you have good demonstration data. For more structured agents, extend the agl.litAgent class. Override the rollout method with your agent logic. LitAgent provides lifecycle hooks for setup and teardown, plus built-in state management. This pattern is ideal for complex agents that need initialization, resource management, or persistent state across training iterations. LitAgent provides lifecycle hooks at every stage. On rollout start lets you initialize per rollout state, like database connections or API clients. On rollout end handles cleanup and logging. Training level hooks on train start and on train end run once at the beginning and end of the entire training process. These hooks give you full control over the agent lifecycle. Your rollout function can return 3 types. Return a float between 0 and 1 as a direct reward value for simple evaluation. Return. None to skip the rollout entirely, useful for invalid inputs or error cases. Or return structured spans, which give the optimization algorithm detailed telemetry about each step the agent took. The span-based return is most powerful for complex, multi-step agents. You can write custom optimization algorithms by extending the algorithm base class. Implement methods like findBestPrompt for prompt optimization or trainModel for weight updates. Your custom algorithm plugs into the trainer seamlessly using the same dataset and agent infrastructure. Always test with trainer.dev first to verify your algorithm works correctly before running a full training job. The Store API supports 2 backends. In-memory is fast and local, but ephemeral, perfect for experimentation and development. MongoDB provides persistent, scalable, distributed storage for production training runs. Both backends share the same API, so you can switch between them with a single configuration change. Start with in-memory for prototyping, then move to MongoDB for serious training. Each rollout follows a lifecycle through the task queue. Tasks start in the queuing state, waiting to be picked up. Then they move to preparing, where resources are allocated. The running state means the agent is actively executing, and succeeded marks a completed rollout. Failed rollouts are also tracked for debugging. This lifecycle gives you full visibility into your training pipeline. Agent Lightning offers 2 execution strategies. Shared memory runs everything in a single process with shared memory, which is the fastest option for development and small training jobs. Client-server enables distributed execution across multiple machines using the Store REST API. Use shared memory for development and prototyping, then switch to client-server when you need to scale up for production training. For distributed client-server setup, you need 3 terminals. Terminal 1 starts the Lightning Store server, which manages all training state. Terminal 2 runs agent workers that execute rollouts and report results back to the store. Terminal 3 launches the trainer that orchestrates the optimization algorithm. All 3 components communicate through the Store REST API, enabling true distributed training. Trainer.dev is your debugging best friend. It runs a single rollout so you can test your agent setup quickly. You get the full execution trace with all spans, making it easy to spot issues. This enables fast iteration without waiting for full training runs. Always use trainer.dev to verify your agent and reward function work correctly before committing to a full training job. The Agent Lightning dashboard provides a visual overview of all training rollouts. You can see reward distributions and trends across iterations. Filter rollouts by status, reward range, or iteration number. Click on any individual rollout to inspect its full execution trace, including all agent steps, tool calls, and the final reward. The Traces view shows detailed execution traces for each rollout. You can see every LLM call, tool use, and decision the agent made. Timing information for each step helps identify bottlenecks. This view is essential for debugging agent behavior and understanding why certain rollouts received low rewards. The AgentOps waterfall visualization shows agent operations in a timeline view. You can clearly see timing and dependencies between steps. Parallel operations appear side by side, while sequential steps flow top to bottom. This makes it easy to identify performance bottlenecks and understand how your agent spends its execution time. Agent Lightning supports OpenTelemetry trace integration. You can export training traces to any OpenTelemetry compatible backend, like Jaeger, Zipkin, or Datadog. This gives you production-grade observability for your training pipeline. You can even correlate training traces with production agent traces to understand how training improvements translate to real-world performance. Agent Lightning ships with several example agents. Spider is a text-to-SQL benchmark agent. CalQIA OCX demonstrates a simple calculation agent. ChartQA tackles chart question answering. The RAG example shows retrieval augmented generation training. And the Unsloth example demonstrates supervised fine-tuning. These examples are great starting points for building your own trained agents. The Agent Lightning community is growing rapidly. Deep Werewolf uses Agent Scope to build a Chinese werewolf game with trained agents. Agent Flow from Stanford brings a modular framework with their Flow GRPO algorithm. U2 Agent has pushed the boundaries with verified 128 GPU scaling for math, code, and search tasks. Join the growing open source community and contribute your own projects. Now let us do a deep dive into a complete end-to-end use case, training a text-to-SQL agent with reinforcement learning. We will use the Spider benchmark, walk through the agent architecture, and see how Agent Lightning takes us from initial setup to measurable improvement in SQL generation accuracy. The Spider benchmark is the industry standard for evaluating text-to-SQL systems. It contains over 200 databases across various domains and more than 10,000 natural language questions. Evaluation uses both exact match accuracy, checking if the SQL query matches the gold standard, and execution accuracy, checking if the query produces the correct results. It is a challenging benchmark that tests an agent's ability to understand complex schemas and generate correct SQL. The SQL agent uses a LangGraph architecture with 4 states. First, the write state generates SQL from the natural language question. Then execute runs the SQL against the database. The check state verifies if results look correct. If not, the rewrite state fixes errors and the cycle repeats. This iterative approach mimics how a human developer would debug SQL queries, and Agent Lightning can train the entire pipeline end to end. The SQL agent is built as a class extending agl.litAgent. The rollout method contains the LangGraph execution logic. The onRolloutStart hook loads the relevant database schema for each task. After the agent generates and executes SQL, the reward is computed based on execution accuracy. This class-based pattern keeps the code organized and testable. The rollout method starts by loading the task, which includes the natural language question, the target database, and the gold standard SQL for evaluation. It builds a prompt with the database schema context. Then it runs the LangGraph write-execute check loop, allowing the agent multiple attempts to generate correct SQL. Finally, it returns a reward based on whether the executed SQL produces the correct results. The reward function uses the official Spider evaluator for scoring. A reward of 1.0 means the generated SQL produces the correct result set when executed. A reward of 0.0 means the query failed or produced wrong results. Importantly, it compares result sets rather than SQL text, so different but equivalent SQL queries both receive full credit. This execution-based evaluation is more robust than string matching. For the SQL agent, VRL is configured with a code-capable base model. You can choose between PPO and GRPO algorithms. Learning rate is typically between 1E6 and 5E6 for stable training. Batch size is tuned based on available GPU memory. The configuration also specifies rollout parameters like max SQL generation length and the number of retry attempts. For training setup, load the Spider training and validation data splits. Configure the trainer with your SQL agent class, the VRL algorithm, and the datasets. Call trainer.fit to start reinforcement learning training. Monitor the reward curve on the validation set to track progress and detect overfitting. The validation reward should steadily increase over training iterations. Here is the code diff showing what changes are needed to train the SQL agent. The modifications are minimal. Add the Agent Lightning decorator and emit helpers. The original agent logic remains completely unchanged. All training infrastructure, the store, algorithm, and trainer lives in separate configuration code. This zero-code change philosophy is what makes Agent Lightning so powerful. The training results speak for themselves. Starting from a baseline accuracy of 56.9%, the SQL agent reached 72.1% after reinforcement learning training. The reward curve shows steady, consistent improvement over training iterations. That is a 15+ percentage point gain achieved with zero changes to the agent code. This demonstrates the power of Agent Lightning for real-world agent optimization. Here are all the references and resources you need. The foundational paper is on RxIV. The source code is on GitHub under the Microsoft organization. The full documentation site has guides, API references, and examples, and VERL, the Reinforcement Learning Engine, has its own repository with detailed documentation. Thank you so much for watching this comprehensive guide to Agent Lightning. I hope it has helped you understand how to train AI agents with reinforcement learning without changing a single line of agent code. Whether you use APO for prompt optimization, VERL for model weight updates, or SFT for fine-tuning, Agent Lightning makes it simple. If you found this valuable, please like and subscribe. Until next time, keep training your agents.